Foundation, Guntur, Andhra Pradesh. With a strong commitment to academic excellence, he has contributed significantly to research, teaching, and faculty enrichment over the past 10 years. His research expertise lies primarily in the domain of physics, with a specialized focus on rare earth ion doped glasses. This niche area involves the study of glass materials that have been doped with rare earth ions such as plasmodium, neodymium, holmium, terbium, europium, erbium, etc. His work investigates their absorption, emission, and luminescent properties, which are the key characteristics for applications in photonic and optoelectronic devices like lasers, amplifiers, and lighting systems. Throughout his career, he has published extensively in reputed national and international journals with over 69 publications and 4 patents, and his work has been widely cited in the academic community, and he is guiding 5 research scholars. He was honored with the Distinguished Researcher Award in recognition of his outstanding contribution to research from KL Education Foundation, Guntur, Andhra Pradesh. His dedication to teaching excellence has earned him the Best Teacher Award 9 times. Today, Dr. M. Venkateshwarlu will be shedding light on how fundamental physics principles derive innovation in engineering materials on the topic physics behind innovative engineering materials and technology, which is crucial for both academic research and industrial advancement. Today, this FDP aims to bridge the gap between theoretical understanding and practical applications by focusing on the evolving contributions of physics in material innovation. As Albert Einstein once said, wisdom is not a product of schooling, but of the lifelong attempt to acquire it. It is with great honor that we welcome Dr. Venkateshwarlu, who truly embodies this wisdom, an educator, a mentor, and a thought leader who has graciously accepted our invitation to share their expertise with us today. Thank you, ma'am.
Recording in progress.
Thank you, Jayachitra ma'am. Participants, you can post your questions in the chat box. Now I invite our chief guest of the day, Dr. M. Venkateshwarlu. Sir, the session is yours.
Thank you, madam, for a nice introduction.
Nice.
Sir, you're not audible.
Now audible, madam?
Yes, sir. Yes, sir.
Yes,
You're
sir.
audible now.
One minute.
You can continue, sir.
I am. So, good afternoon to everybody. This is Dr. M, Department of Physics. Welcome to all for 5-day faculty development program on materials. And today's my presentation on physics behind innovative engineering materials and technology. This is the view of my university. It is situated at Guntur. So nowadays we know the materials are probably more deep-seated in our culture than most of us realize, like transportation, housing, clothing, communication, recreation, food production, etc. So every segment of our everyday lives influenced to one degree or by materials like metals, plastics, glass, and fibers. So every day our life is completely depending upon the materials like recreation. So materials enhance our recreational activities and experiences, clothing, transportation, food production, communication, and housing. So from starting onwards for early human beings is depending upon the different stages of the materials. Like stone age, at that time, the early human beings is depending upon the stone, wood, clay, and skins. So later stage is the bronze stage, then iron. Now it is the silica age. So you can observe here in early human beings. So initially they are lives in forest, so they don't know about the materials, but they're used something for the protection, like for the protect from the seasons. They are used the skins as a cloth or leaves. Okay, so later they are used the stones for hunting the animals for food and observe that animation. So for wheels, they are prepared using the uh, stones like a tire, or it is in a circular shape. Okay. So whenever they need something, they are thinking for the new materials, like innovative materials. So next is the bronze age. So stone is limited to the few tools. Later is the bronze discard, and bronze is nothing but a copper and tin alloy. So using this bronze material, they are making more number of tools stronger, durable, as well as increased the productivity in agriculture and hunting and all. So bronze is not only that. So the kingdoms are used to prepare the weapons and all. So you can observe here. So this is about the stone age. This is the bronze age. Later is the iron age. So the people are start using the iron to prepare the silica age, because the silica play a vital role in our day-to-day life. We know that with the vacuum diodes, so occupying a large volume. Okay, so to construct a one keyboard or one monitor or one CPU, it occupies the lot of space. So they are unable to move the system from one place to another place, and number of systems constructed is very limited. So because cost is more and occupying the more space and all. Okay. So later the burden is of one of the physics scientists is constructed the silica diode. So the silica diode size is order of the millimeters. So the total vacuum diode size is order of the meter cube volume reduced to a millimeter size. So according to that, the volume of the CPU or monitor, everything is reduced to the
Sir, you're not audible, sir. Excuse me, sir. Your voice
Sir,
is
you're
not
not
audible.
audible. Uh, PPT slides are moving, ma'am.
I think
Yeah.
so. Somebody is muted.
Excuse me, sir.
Side is moving.
No, sir.
No, sir.
Yeah, madam.
It's in the
Am I
first
audible?
slide, sir.
Am I audible?
You're audible, sir.
It is in
Yes, sir.
first
You're
slide.
audible now. You're audible now,
Okay.
but it is in the second slide, sir. Your campus is
It is in
shown.
seconds. Okay, 1 minute.
Go to slideshow. Slideshow, you can switch on.
If you prefer
1 minute,
slideshow, it
ma'am.
will be better, sir. Yeah, your video is
Yeah.
on. The slides are not shared, sir.
1 minute. Share the window. Okay, share.
Yes, sir.
Now it is audible, madam.
Yes, sir. Audible and video is shown, sir. Second slide, third slide is
Oh.
there. Yes, sir.
Sir, actually, you can go to the slideshow mode, sir. So one after the other, we can see.
Yeah, madam.
Slideshow.
It is
Yes,
slideshow
fine.
mode. It is slideshow.
So individually, we can see the slides now, sir.
Now it is in slideshow, madam.
No, sir. It is not yet, sir.
Oh.
Has started screen sharing, but the screen is not shown, sir. Your video is on.
Yeah, video is on, madam.
Yes, sir. The video is on. You're audible, but the screen is not shared.
Window is shared.
Yes, sir. Now it is the slide. Third slide is shown, sir. You can continue, sir.
Without slideshow, madam.
Yes, sir. Third slide. Materials are probably more deep seated. That slide is shown, sir.
Yeah.
You can continue, sir. You can continue. Thank you.
Okay. So materials are probably more deep seated in our culture, day-to-day life, materials in transportation and food production. Now it
So it's in the third slide. You have to move on to the fourth slide.
Sir, you're not audible, sir. Now your mic is switched on.
but why it is changing to mute mode? I don't know. Okay. Okay. Anyway,
You're audible, sir. You can continue.
Shiva, ma'am. You have unmuted. The message is showing that you have unmuted, sir.
madam, why it is continuously going to unmute? I don't know. So when I am talking, it is undergoes to unmute.
Yes,
Mute
sir.
mode.
Now you're audible, sir.
Okay, okay, madam. Now slide is changed, madam.
Yes, sir. Stone Age, Bronze Age.
Yeah.
Yes, sir.
So
That is the slide.
different stages of the materials used by our early human beings. Is the first stage is the Stone Age. So at the time, the people are used the stones, wood, clay, and skins. So later on, the materials are developed into Bronze Age. So at that time, the people are used the bronze. Later, it is the Iron Age. Then it is the Silica Age nowadays. So you can observe that our early human beings are used the stones as a weapons, as well as for the transport purpose. they are prepared the stones as a wheel. And later, it is the Bronze Age. The Stone Age is limited to the very less tools. Now, bronze is the developed is the mixing of the copper and tin. So it is enhanced the strength of the materials as well as durability is also more. So later it is incorporated into agriculture and hunting purpose also. So bronze is the advanced materials than the Stone Age, and they are utilized for the war purpose also. So these are the different stages and their uses of the materials in step by step. So later bronze stage it is the Iron Age. So the human beings are is start using the iron, and later now is the Silica Age. So this is the Silica Age because whatever the electronic instrument or electronic gadgets which consisting of a either diode or transistor or integrated circuits, without those there is no electronic gadgets. So nowadays our all lives are depending upon the electronic gadgets like computers or projector or air conditioner or washing machine, televisions, like that, have a many number of electronic gadgets leading to our comfort life. These are all is nothing but a advance in the materials. And the role of physics is quantum mechanics, thermodynamics. Now come to the condensed matter physics. In that we are having mainly crystallography. So crystallography is nothing but they study the arrangement of atoms inside the crystal, how the atoms are arranged. So the array diffraction techniques, and later the crystal defects or imperfections play a important role in the advancement of the materials. For example, we know semiconductors. So semiconductors, a pure semiconductor is the insulator at absolute. Audible, madam?
Yes, sir. Yes, sir. The slides are moved. Yes, sir.
Pure semiconductors are insulators, but applications are very limited. But by doping with the trivalent or pentavalent group atoms, we can N-type semiconductor and P-type semiconductor. So by using N-type and P-type, we can construct the diode or transistor. So nowadays we know that applications of the diode and transistor in every electronic gadgets. So these diode or transistors can be act as sensors, optoelectronic devices, optical devices, like that many number of applications in our day-to-day life. So like the details of the X-ray diffraction is used to reveal the structure of the materials, and crystal structure, arrangement of atoms how inside the material, and also by doping with the different materials into that. So next one is the semiconducting materials. So by understanding the structure of the materials, band structure like valency band, forbidden band, and conduction band. So based on that band structure or band gap, so materials are classified into conductors, semiconductors, and insulating materials. So conductors, valency band and conduction band is partially overlapping. So electrons are already is valency band is overlapping with the conduction. So those electrons are participated in electrical conductivity. So in semiconductors, the band gap is less than the 2 electron volts. So less amount of energy is required to exert the electron from valency band to conduction band. Whereas insulator, it has a large gap between the valency band to conduction band. So in this case, each material have their own applications. So generally the people are talking conductors are having more applications or semiconductors than the insulator. No, everywhere, whatever we are used the conductor, at that place insulator is also required. Otherwise, we can't sustain our lives on earth. So it has the equal importance of the insulator to the conductor or semiconducting materials. So similarly, altering the band structure by doping or alloying. So for example, we can say semiconducting materials like gallium arsenide, trivalent and pentavalent group atoms. So by the combination of the trivalent and pentavalent group atoms is known as a compound semiconductor. So by doping with a few more trivalent adding to the one, we can change the band width, that is forbidden band gap. So whenever the forbidden gap is changed, the emission wavelength is also changed. We know that E equal to h mu and mu equal to c by lambda. So E equal to hc by lambda and lambda equal to hc by Eg. So from that we can say that band gap and wavelength is both are inversely proportional. So by alter the band gap, the emitted wavelength is also changed. So based on this concept, nowadays we are having different types of color LEDs, light emitting diodes, by using gallium indium phosphate, gallium arsenide phosphate. So like that, by using the one more element with the combination of the third and fifth group, we are getting the different colors of LEDs. So these are all some of the is the solid state physics and magnetism. We know that okay, ferromagnetic application, magnetic applications also there. Okay, so like if storage devices like external hard disk or floppy drive. Okay, so previously are having magnetic tapes while recording in a recorder, tape recorder like that. In olden days, we are using that all those things. And superconductivities play a very very important role. We know that Maglev vehicles or super fast trains is the magnetically leviated vehicles. Magnetically leviated vehicles in the sense, so the track is in magnetism and bottom side of the vehicle they are arranged the superconducting magnetic material. In superconducting state, that magnetic material can be act as a diamagnetic material. So diamagnetism and magnetism both are repelled. So the trains are lifted into the air about 15 to 20 centimeters and it is help to moving in forward. So there is no friction between the wheels and track. So the velocity is almost all 550 kilometers per hour. So to stop the train, gradually they're increasing the temperature of the diamagnetic material. Then it is converted into normal state. So like that, they can run the Maglev vehicles based on the superconductivity. In MRI scanning, magnetic resonance images, they are used the superconducting materials. And another one is the SQUIDs, superconducting interference devices. So SQUIDs are used to identify the heart attack or the brain system, how it is working. And all those things can be monitored using SQUIDs, superconducting quantum interference devices, is related to the physics concepts. And chemical reactivity, thermal stability, strength, bond, all these things is related to quantum mechanics and is a cycle wise heat transfer, phase transitions, and all those are the physics concepts. Okay, So electromagnetism in material like optical of light and converted into energy. So like that, optic and electrical energy in an electric field like capacitor plates. We can enhance the capacitors. All are about talking the supercapacitors and electronic components and all those things is the depending upon the dielectric properties of material. And development of the semiconductors. So recognizing the vectors and by doping with the materials, it is converted into N-type and P-type, as well as a compound semiconductors like a trivalent and pentavalent group atoms, gallium arsenide, or second and sixth group element combination is also called as a compound semiconductors. So these are the elemental semiconductors or N-type and P-type extrinsic semiconductors and compound semiconductors. Each one have their own applications. Okay. So apply these principles to understand the behavior of being the different elements, then transforming this electronic industry with new technologies like transistor, and it can be act as a sensors and all. So optical properties and laser operations. So whenever the light is incident, light is nothing but a electromagnetic waves. So light is incident on a material, it undergoes to maybe absorbed by the material or reflection of the light from that, or it is transferred, transmitted through the material, or the light is scattered at the lattice ions or atoms. Okay. So in this process, we are having absorption, spontaneous emission, stimulated emission, and population inversion, cavity device. So these are nothing but a construction of the laser. So when light is incident on the object, so whatever the atoms are present in a ground state, those atoms are absorbed that energy and excited to higher energy state when the incident energy must be equal to energy difference between the two states. That delta E is nothing but the energy difference between the two states, then electrons are excited to higher energy state. This process is known as a stimulated absorption or absorption. Once it is excited to higher energy state, that electrons or atoms are stay up to some time, that is the lifetime of the excited state. So generally lifetime of the excited state is order of the 10 power minus 8 seconds. After that, maybe voluntarily it is a de-excited to lower energy state is known as a spontaneous emission. But here is the triggered with the external agent, then it is coming to the ground state and emits the two photons, that is known as a stimulated emission. Those two photons are travel in the same direction is the directionality. Both are having same wavelength is the monochromacity. And when both are in same phase, then crust and trough and troughs are superimposed to each other. Result and high amplitude is occurred. When a high amplitude means a high intensity of light is coming out. So it means the directionality, same wavelength or frequency, monochromacity, and coherence, then high intensity. These are the characteristics of the lasers. So compared to the ordinary light, the laser has some special characteristics. Those are given by directionality, monochromacity, coherence, and high intensity. So these are the characteristics obtained by the stimulated emission. So to obtain the stimulated emission, we need population inversion. Population inversion means generally the ground state number of atoms is more when compared to the excited state. But when it is excited state is the metastable state, Metastable state means the lifetime of the excited state is more than the 10 power minus 3 seconds. Means the excited atoms spent more time. So the more number of atoms are accumulated on the excited state compared to the lower energy state at a particular time. That is called the population inversion. So once population inversion is occurred, then it is triggered with the external atoms or external photons. That is called the stimulated emission. So due to the stimulated emission, we are obtain the laser. Then for that, we need a cavity design. That cavity has a certain length and end faces are act as a optical resonators. So because the emitted photons are travel in between the two end faces and it makes the collision with the metastable state atoms, resultant it leads to the stimulated emission. So finally is coming out from the partially reflected surface that can be treated as a laser. So these are the applications of the lasers, the different like ytterbium, neodymium, eurobium, holmium, thulium, praseodymium, cerium, etc. These are the some of the rare earth elements. We know that total 17 rare earth elements are there. So based on the emitted intensity or power and wavelength, they can use for the different applications like industrial, medical, military, telecommunication. So like that, having many number of applications in various fields. So at the end, we will discuss the applications of the lasers in various fields. Now, I would like to present my research work. So investigation of the change in structural luminescence properties of dysprosium, terbium and dysprosium terbium co-doped zinc bismuth barium borotelluride glass system. So the research gaps are finding the new host glass for the photonic applications, and it has a low melting temperature, low phonon energy, high emission cross section, high quantum efficiency, used for lasing and photonic applications. Okay, so here the borate glasses is a glass former He3BO3 or B2O3. It has a good optical transparency and good thermal stability, mechanical stability, and high gain bandwidth. So, but the drawback is borate have a high phonon energy and a high melting point. So to reduce this phonon energy and melting point, it can be added with the tellurium. So tellurium have a less melting point and low phonon energy. So in addition to that, to reduce the phonon energy is a combination of the heavy metal oxides or fluorides. So these combinations is reduce the phonon energy as well as that melting temperature. Phonon is nothing but a thermal vibrations of the lattice ions. So phonon energy is more, mechanical vibrations is more, then photons energy is less. So to overcome that, we can add the heavy metal oxides and fluorides. Okay, so these are the objectives, and we have followed the melt quenching technique method. Okay, so melt quenching technique method is nothing but first that material is heated to the certain temperature, then it is converted from solid state to liquid state. Once it is in liquid state, we can pour this liquid on the free heated brass plate. It means suddenly reducing that high temperature to room temperature. When it is reduced to room temperature, then it forms a glass. This is called the melt quenching technique. So in this, I have considered the 5 mole percent of the ZNO, 5 mole percent of the Ba2O3, 15 mole percent of the BaF2, 65% of the B2O3, 10% of the tellurium oxide, and some X percentage of the dysprosium oxide Dy2O3. So by increasing the dysprosium oxide Dy2O3 percentage, and the same amount we can reduce in the B2O3. So that dy2 concentration 0.5 mole, 1 mole percent, 1.5 and 2.5 mole percent. And corresponding we are reducing the B2O3, and we are prepared the different concentrations of the dy3 doped glasses. So first we are taken in a molar percentages, total 100%, and those chemicals are weighing in the electric balance, and it is grinded into a fine powder in agate mortar around 1 hour for getting uniform mixture, and that mixture is taken into the silica crucible. It can be to stand up to 1200 degrees Celsius temperature. Now this silica crucible is placed in a 4-grammable furnace up to 1150 degrees Celsius. So at this temperature, that material is converted into liquid state. The liquid is a melted liquid is poured on the free-heated brass plate, and it is pressed with the another brass plate, and finally it form a glass. So these glasses are placed in a uh, annealing purpose in a at 350 degrees Celsius for 1 day. So to reduce the thermal strains in a material. So this is the melt benching technique to prepare the glass materials. And once we are prepared the material, so as a material scientist or physicist or chemist, first we have to know whether the prepared material is the crystalline material or amorphous material. So now we have recorded the XRD spectra for the prepared glass samples, and it is a broad hum is nothing but a prepared sample is the amorphous material. And here we can observe the a few peaks at 20 and 50 degrees. It is due to the nano-sized crystalline materials are present in a prepared glass sample. If it is completely crystalline, then we are getting these sharp peaks related to each plane. But here we are obtaining a broad hum which is related to amorphous materials. So next one, to know the bonding nature, we have recorded the FTIR. So from that, so we can identify the bands at wave number is around 566, 764, 1132, 1488, 2365, 3458. So these bands is corresponding to the bonds existed between the various atoms that list here given. So next one is the absorption spectra. So in this, the recorded glass is placed in a VV visible NIR spectrometer, and the suitable wavelength from 200 to 2000 nanometers of the wavelength is passing through the glass sample. Then corresponding it is absorbing the energy and excited to some states, and that states are represented corresponding to wavelength, and from that we are getting the energy. So for that energy it has a certain states, energy states. These states are identified using the Carnot matrix paper, and from this, by measuring the area of this each peak as well as X dispersion and Y dispersion, we can measure the oscillator strength of the materials, F experimental and F calculated. So based on using this F experimental, and as well as we can use the refractive index of the materials, we can measure the uh, judo offlet parameters. So here three important parameters: omega 2, omega 4 and omega 6. Omega 2 represents the covalency nature of the rare earth to the surrounding ligands, and omega 4 represents the viscosity of the material, and omega 6 is represents the rigidity of the material. So in this case we are obtained the omega 2 is greater than omega 6 is greater than omega 4 trend. That indicates that the covalence nature between the rare earth ion to uh, ligand like boron or bismuth and all. And omega 6 is the rigidity is more than viscosity. So this is the trend is a followed. So out of that prepared different mole percentages, 1 mole percent of the glass are having that more values. And these values are compared with the literature also. And next, once it is over, then we are considered the excitation spectra. So in this excitation spectra is emission wavelength 575 nanometers is used to record the excitation spectra. This excitation spectra consisting of a total 8 bands. Out of that, so at 386 nanometers having more intensity. That indicates that at that particular wavelength, the more number of atoms, rare earth atoms are absorbed that energy and excited to 4813 by 2 state. So this wavelength is used to record the emission spectra. So the emission spectra is recorded at excitation wavelength of the 386 nanometer. So in this case, we are having, so these 4 bands are occurred, out of which it is 6H15 by 2 and 6H13 by 2 is a more intensity peaks. And these peaks those wavelengths are used to evaluate the a few parameters. Like, so we are calculating the transition probability, total transition probability, effective bandwidth. From that, emission cross section sigma SE into delta EF, branching ratios, experimental branching ratios, and all. If sigma SE, that is emission cross section, is more, then those are suitable for the lasing materials. And branching ratio is also more, those materials are useful for the lasing materials. So in this case, that 1 mole percent of the materials are suitable for the lasing materials. And this is the energy spectra. So in the excitation, we are having a particular wavelength. So that is 386 nanometers. And the non-radiative transition is taken from 4I13 by 2 to 4F9 by 2. From that 4F9 by 2, it makes different transitions. So in this, these transitions are there. So corresponding 481 nanometer, 575, 665. So these are the wavelengths is corresponding to green and yellow colors. So this is the decay curves. So decay curves indicates that how much time those ions are spent in the excited state. So if lifetime is more, then have a leads to the stimulated emission. And this is corresponding to 1 mole percent. We are getting the quantum efficiency is more. Quantum efficiency is nothing but tau experimental by tau calculated. And similarly, sigma S emission cross section is also more. And these values are compared with the literature survey. And this is the chromaticity diagram, and as well as this is the confocal images. So when we are recorded these confocal images, the light is approximately at the white color. It is lies on the near to white color. So color chromaticity coordinates are measured. Those are X and Y, and those values are represented in the chromaticity diagram. And the second one is the terbium. And terbium is the same. We have followed the trend, the same concentration mole percentages, as well as terbium ion 0.5, 1.5 to 2.5, like this. So it is taken in a molar percentages and grinded into a fine powder for 1 hour. And then it is taken into the silica crucible and placed in a 4 gram bull furnace. And after heated to the 1 hour, then it is transferred into the preheated brass plate and melt quenching process. Then finally graphs are prepared. So then we can consider the absorption spectra. So here we are having mainly 3 peaks at 485 and remaining 2 are the in infrared region. So as usual, we can calculate the oscillator strengths. Those oscillator strengths are used to measure the Judo-Offlet parameters. And you know that Judo-Offlet parameter, omega 2 is indicates the covalency nature. Omega 4 is the viscosity and omega 6 is the rigidity. And once we can absorption is completed, then we go for the excitation spectra. So at emission wavelength of 542 nanometer, we have recorded the excitation spectra. In that excitation spectra, at this particular wavelength, we are getting the maximum intensity. So that wavelength 377 nanometer is used to record the emission spectra. So in that emission spectra, it contains 4 peaks or 4 transitions. In that around at around at 500 nanometers, it has a high intensity. Okay, so using those emission spectra, we have recorded the this transition probability, branching ratios, emission cross sections, and all. So those parameters are represented here. And these studies, as usual, we are compared with the other works, and we are getting the maximum value for the 2.0, and beta experimental is 64, and that sigma SE is the 14.61, and it is compared with the literature survey. And this is the energy level diagram for this. At 377 nanometer is the maximum intensity for the excitation spectra. And this is the non-radiative transition. It takes place from 5D3 to 5D4. So from that 5D4, it makes the different transitions to the different energy levels. So in that around 489 is the one peak, 543, 585, and 622 nanometers. And this is the exponential decay of the terbium doped glasses. And for this, we have calculated the tau experimental, tau R, and quality factor. So then we are having RCCDA and quantum efficiency. So this 1 mole percent have a highest quantum efficiency, that is 73%. And this one 2.5 is the 90, it is the maximum for these prepared glasses. Okay, so again we have draw the CAE chromacity diagram. So in this you are observing that it is lies in the near to the green region. It is lies in the green region. So then again we are taking the co-dopants. Previously we are considered the individually dysprosium doped as well as terbium doped. Now we can combine these and we can make a dy 1 mole percent getting the maximum parameters like quantum efficiency or omega 2 and all. So 1 mole percent is the fixed one, and we can vary the terbium doped material with 0.5, 1, 1.5 to 2.5 up to that. And as usual, we can follow the melt quenching method to prepare the material. And this is the excitation spectra for the terbium and dysprosium doped glasses. So in this case, we are used the 575 nanometer as a emission wavelength for the dysprosium and 544 nanometers as a emission wavelength for the excitation spectra of the terbium. So and both are represented here. So this green color is the TB and this orange color is the dy excitation spectra. So in this case, we are obtained the maximum intensity for this. One is at around 386, is another one is at 386, another one 377. And those wavelengths are used to record the emission spectra. So these are the emission spectra are recorded at 366 as well as 388 nanometers. And you can observe that, so at 360 nanometers, we are getting the maximum intensity when compared to this. And this is the Y by B ratio. So in this case, yellow2 is the bluish we are taken here, or a green color is based on the emission. So this one is the yellow and this is the green. Now these ratios we are taken here, the intensities. So for two diagrams we are considered here at 366 as well as 380 nanometers emission spectra. So if you observe this, so in this case, this increment in the green color when compared to the yellow is more in case of the 388 nanometer excitation wavelength. So at this wavelength, it is suitable for the emission of the uh, white light. So this is given by uh, energy level diagram for the both spectra depending upon that 366 as well as 388 nanometers. And these are the corresponding to the decay curves. And these are the corresponding to the CAE chromaticity diagram. At 380 nanometers, you can observe carefully. This is the white light, and these are, it is increasing from white light region to gradually shifted to the green color. And again, it is that 4 more, I mean 2, it is the maximum, and remaining 1, 2, 3 is near to the white color. And similarly, you can observe that at 366 nanometers wavelength, so this is shifted from white light to complete green color, complete green color. So depending upon which light is required, either white or green, we can tune the colors by doping with the different concentrations of the rare earth ions. So as usual, from the emission spectra, we have calculated the this emission colors and CP, effective bandwidth, color coordinates and all. So finally, we have prepared successfully zinc, bismuth, barium, boro, fluoro, telluride glasses is activated with the dysprosium ions by melt quenching technique. So as well as we have prepared the same glasses by doping with the terbium and co-dopants of the dy and Tb, and successfully characterized the XRD, FTIR, absorption spectra, excitation and emission spectra, as well as decay curves for all these. And depending upon the type of the ion, we are obtain the different colors like dy doped, we are obtain the white light, and Tb doped, we are obtain the green. And by doping with the dy and Tb combinations, it shifted from white light to green color, and based on the concentrations as well as excitation wavelengths. We can observe carefully in case of this. So only terbium, it is taken at 366 nanometer excitation. So it is shifted from white light to green color. Whereas in this case, so it is gradually shifted from white light to this one. So okay. So like that, we can tune the colors by doping with the rare earth ion concentration into the glasses. So finally, So terbium doped, we are obtained the green color light, and by dysprosium doping, we are obtained the white light. And in case of the DY-TB combinations, we are obtained the light shifted from white light to green color. And these are the we have recorded while taking the PL spectra for the various ions. So UU ions, so it is emitted pink color almost. For SM it is the orange, and holmium it is the uh, green to blue color, and dysprosium is the white color, and terbium is the green color. You can observe clearly. So these are the colors are emitted by the prepared glass samples. So now how the technology is transferred. So in olden days, first we are having a typing machine to type the letters on a white paper. So later we are having dot matrix printers. It takes a lot of time to print the dot by dot. Later it is the line printers are there. Line by line it will be printed on the ribbon. So it's take a lot of time to take the one printout. Maybe it's take typing machine is 10 minutes around. In case of the dot matrix printers, it is 3 to 4 minutes. That inkjet printer is maybe take 1 minute. Nowadays, all we are using the uh, laser printers. Around 10 to 14 copies are coming out for the minute time. So that is due to the development of the materials from day to day. It's not happened in a overnight. It takes many number of decades. Okay, so these are the different types of the printers. So in all those things, we are used the electromagnetism and lasers. So in first one, it is the sorry, 1 minute. So first one is the mechanical energy we are used in that. So then storage devices. So in olden days around 2000, when I'm doing my MPhil work, I have used the floppy drive. So the floppy drive storage is only 1.4 MB. That is based on the recording by using the hard magnetic materials. And at that time, hard disk in the computers is the magnetic materials only. Okay. So later we are having CD, compact disk. The floppy drive, the storage capacity is only 1.4 MB. It's a very less amount. Whereas in CD, you can observe that it is the storage capacity is a 700 MB. Means 500 into 1.4. Means the storage capacity is increasing to 500 times. And cost is the floppy drive is around 14 rupees or 15 rupees, whereas CD cost is available from 7 to 10 rupees. Means cost is reduced to half and storage capacity is increasing to 500 times. So the data storage on the drive using the magnetic needle or lasers. Nowadays we are used lasers to read and write the data in CD, as well as DVD. 4.7 GB is the enormous storage capacity when compared to the floppy drive and Blu-ray. Okay, so like that we are having the day to day the improvement in the technology. That development of the technology is due to the science, advanced materials only. Okay, so nowadays we are having SSD card as a memory card and USB pen drives. This is the flash memory like that. So from floppy drive to nowadays we are using the SSD cards. That is all due to the development of the advanced materials by physicists or chemists or material scientists. And just we can look at here. So here we are having different lamps: incandescent lamp, halogen lamp, CFL bulbs, and LED bulbs. So here the light intensity is the lumens. So 450, 800, 1100, and 1600. Say for example, 450 lumens to produce that, incandescent lamp required 40 watts power, whereas a halogen lamp is 29 watts, CFL bulb is 9 watts, and LED bulb is 7 watts. For same intensity, but the power required is less in case of the LEDs. So the development of these bulbs from stages by stages is not in a overnight. Okay. Similarly, highest 1600 lumens is produced by 100 watts power is required for the incandescent bulb, whereas for a halogen 72, CFL 23, and LED is a 20. So nowadays is the 20 watts LED bulbs or 0 watt bulb, 7 watt. Most of them we are using the LEDs because the power consumption is very less when compared to the halogen lamp or incandescent lamps. So equipments are available in our university. Is the XRD and this is the FTIR. These two are purchased under the DST FIST. Level 1 is the 1.07 crores. And we are having electronic balance. Electrical furnace, we are having 1700 degrees Celsius infra furnace, 1400 degrees Celsius, as well as 1000 degrees Celsius infra furnaces are available. And as well as hot air ovens are available, and electrospinning unit, electrochemical workstation, ultrasonic interferometer, spray pyrolysis equipments are available. And these are the equipments are available: electronic weigh balance. This is the magnetic stirrers, Abbe refractometer, vacuum oven, and this is the monochromator, and with various lasers, 410 nanometer and 980 nanometer low. So this is the visible, and this is in the infrared region, and this is the terbium doped is emitted the green color, and this is the U is the pink color is emission. This is the JASCO PL spectrometer, and these are the atmospheric science lab and having these equipments with us. And so far I have I'm guiding the 5 scholars. One scholar is awarded, and these 2 scholars, VRL Murthy and Sumalata, is submitted their thesis and waiting for the Viva awards. And this Naveen is completed his papers, and departmental talk is completed. We are going to conduct the pre-talk coming soon. And is the one more employee is the retired SBI. His own interest is doing this PhD under my guidance. We have started the new work in polymer electrolytes, biopolymer electrolytes. And thank you all. And thanks to management of the New Prince Bhavani College of Engineering, and thanks to head of the department as well as convener and co-conveners of the 5 days FDP on role of the physics in development of advanced materials. Thank you all.
Thank you, sir. Now, questions posted on the chat box will be handled by Dr. K. Jayachitra. Over to you, ma'am. Jayachitra, ma'am.
Okay, ma'am. 1 second, ma'am.
Okay, ma'am.
Thank you, sir. Thank you very much for your insightful session. We now open the floor for a question and answer session. We kindly invite you to engage with our participants and address their queries. Your thoughts and clarification will surely enrich our understanding further. The first question is, what are the typical post glass materials used for rare earth doping?
We are having many glasses like silicate glasses, germanium glasses, borate glasses, tellurium glasses, like that in glass materials. Germanium and silicon having high melting point around 1600 to 700, 1700 degrees Celsius, as well as high phonon energy also. And boron glasses are having around 1200 degrees Celsius melting temperature and is a moderate phonon energy. So to reduce that phonon energy, we can dope with the heavy metal oxides as well as fluorides.
Second question is, which is the best storage device?
Nowadays, we are used the storage devices is the SSD cards. So as well as gradually we are changing from the magnetic materials to SSD cards.
Next question, how does the local environment in glass affect the radiative and non-radiative transitions of rare earth ions?
Yes, it's a very good question. So actually, the rare earth ions consisting of a compactable energy levels, closely spaced energy levels. So it is the common. But when we are doping with the different uh, types of base glasses like tellurium or borate or silicate glasses, it change the environment. That environment is affect the intensity. Intensity means that more number of atoms are excited from lower energy state to higher energy state. Again, they will come back and emit the laser. So far, the commercial lasers like ytterbium, doping with aluminum is more commercialized.
Next question, how do the principles of quantum mechanics and solid state physics contribute to the development of innovative engineering materials such as superconductors, nanomaterials, and smart materials for modern technology?
Yeah, nowadays is the all are talking about the quantum valley. So in quantum valley, we are having quantum bits and bytes. That leads to the new technology nowadays. And supercapacitors is also play an important role. Is nothing but a dielectric materials. So dielectric materials by polymer dielectrics play an important role nowadays to prepare the supercapaciting materials. And recently we are transformed to the new nanomaterials also play a very, very important role nowadays in almost all. So nanotechnology is also is gradually lagging. Now all are running towards the quantum valley.
Next question, smart materials can heal themselves, change shape, or respond to their environment. What basic physics ideas help them to do all this?
Smart materials is based on the environment, like is the shaping altered is based on the temperature as well as environment and what type of materials we are used in that, and all those things is responsible for the uh, smart materials properties.
Next question, what are the challenges in achieving population inversion in rare earth doped glasses?
So challenges in the sense we need at least one metastable state. So metastable state means the lifetime of the excited state is more than the 10 power minus 3 seconds. If lifetime is more, then whenever these atoms are excited to higher energy state, they can spend more time in that excited state. So at that time, that photons is the trigger the metastable state atoms, then it is coming to the ground state, and they are emitted at a time more number of photons with the same direction, with the same phase. So then only stimulated emission is occurred, then it leads to the laser. So metastable state and population inversion play a crucial role in the development of the lasers as well as cavity design also.
The next question is, which luminescent materials are better, powder or glass?
Yes, glass is also better as well as powder. Like in case of the LED, the POSPAR materials are coated on the surface of the LED bulb. So to convert the blue light into different color lights. So their own importance is there. We can't say this is the only is important. So nowadays, glasses next is leads to the POSPAR. Then BioPOSPAR materials also nowadays we are preparing. So based on the application.
Next question.
Jayachitra
What
ma'am.
allows
Jayachitra
biopolymer
ma'am.
electrolytes?
Jayachitra ma'am,
Yes.
since we have to start the English faculty development program, can we post the questions to the in the group to sir, and then we can get the answers and send it to them.
Okay.
Yes, yeah, because the other session has to start by 4 o'clock. Sorry, sir, to interrupt.
No problem.
We have another FDP at 4 o'clock. They have to join in the same link. That is a problem for adding
Okay. Okay, no problem.
So,
Okay.
yes,
Ma'am,
yes,
excuse me, ma'am.
Yes, ma'am.
Sir, thank you so much, sir, for joining us.
Thank you, madam, for giving this wonderful opportunity. And
Yes,
let
sir.
me congratulate all the conveners and co-conveners and management. Thank you, madam, for giving this wonderful opportunity.
Thank you,
sir.
sir.
Now
So actually, we are happy
now I
that
invite
we have seen so many sample preparation tools available and the characterization tools available in your institution.
You should,
So,
madam, we are ready for the collaborating with anybody. We are all welcome to you to prepare the samples or characterization, anything. So
okay,
my
sir.
mail ID is mvrmphil, mvrmphil@kluniversity.in or mvrmphil@gmail.com. You can contact me.
Okay, thank you.
Okay, thank you, ma'am. Thank you.
Now I invite Dr. K. Jayachitra to render word of thanks for this FDP program. Over to you, Jayachitra ma'am.
Gratitude is not only the greatest virtues, but parent of all the others. As we come to the conclusion of this enhancing faculty development program on physics behind innovative engineering materials and technology, it is my privilege and honor to deliver the vote of thanks on behalf of the organizing team. First and foremost, I extend our heartfelt gratitude to our distinguished speaker, Dr. M. Venkateshwarulu, who shared their invaluable knowledge and expertise with us over the course of this program. This session provided a comprehensive view of the role of physics in the development of advanced engineering materials, as well as extremely beneficial in understanding the fundamental physics that govern the behavior of emerging materials like smart materials and metamaterials. It highlighted current research trends and opened up new perspectives for collaborative research. We are deeply thankful to our respected chairman, K. Loganathan, Vice Chairman, L. Naveen Prasad, Director Professor A. Swaminathan, and Principal Dr. P. Saravanan, and Head of the Department of Science and Humanities, Dr. S. Swakami, for their continuous support, encouragement, and visionary leadership, without which this program would not have been possible. A special note of appreciation goes to the organizing committee and coordinators for their meticulous planning and seamless execution of every aspect of the FDP. Your hard work and dedication deserve much applause. To all the participants and faculty members, thank you very much for your active engagement curiosity, and thoughtful interactions. Your enthusiasm contributed greatly to the vibrant learning environment we experienced throughout this program. Once again, thank you all.
Thank you, ma'am. To conclude this third day of faculty development program, I sincerely thank all the participants, and you can join tomorrow for another talk by Dr. Vijay Kumar Parandaman, Postdoctoral Fellowship, Universal Tenaga National, Malaysia, on the topic two-dimensional PT-like materials. We are expecting your kind cooperation and participation. Thank you all once again. You can leave the meeting now.
Participants are requested to fill the feedback form, which is given in the chat box. To switch on your video to take a screenshot. And if participants are available, you can also share your video screen. A special thanks to all the participants who are joining with us during the holiday also. Chitra ma'am, Shiva ma'am, and Beulah ma'am, I request you to turn on your videos. Chitra ma'am. Chitra ma'am, can you hear me?
Yes. Yes, ma'am.
Ma'am, you kindly post the email ID of Sir Venkateshwarlu sir in our WhatsApp group, ma'am, so that our participants can contact if they need for any characterization
Okay, ma'am.
technical
Okay.
tools. Chitra ma'am, your video is not available. Beulah ma'am and Shiva ma'am,
Yes,
can you switch on your videos? Just for the documentation purpose, it's required. Beulah ma'am? I think she left the meeting, huh? Okay, thank you, ma'am. You can turn off your videos.
yes, ma'am. Beulah ma'am is not here, ma'am.
Yes, ma'am. Okay, ma'am.
Okay.
Thank you. You can turn off your videos.
Yes, ma'am.
Participant lead the meeting so that we can able to know how many want to do it. Still. So we have so far 146 feedback responses. Shiva ma'am,
Ma'am,
since English is starting now around 4
So,
o'clock, we can leave the meeting.
okay, okay.
Okay. Thank you.